Welcome Regents physics students. Today's topic is something called total internal reflection and critical angle. But before we begin with today's information, I want to just point out something that I actually forgot to mention in the last video lesson, Optics 4. So, in Optics 4, we learned about how light bent when it went from one medium to another. So what I have here is light coming from air and going into glass. The light bends away from the normal. In other words, theta 2 is smaller than theta 1. You can calculate those angles using Snell's law on the reference table. Okay? But why does refraction happen? Why does the light bend like this? It comes in, it does not go straight, it bends towards the normal when we go to a higher index. Remember that we learned 2 lessons back that light changes speed when it goes from one index to another, one substance to another. The formula is n equals c over v. The bigger the index, the smaller the speed must be, because speed is in the denominator. So when I go from air to glass, light is slowing down as it enters the glass. This is the reason why it bends. I have here just a piece of paper I colored red, represent like a laser beam. A lot of time lasers are red. But remember that a laser ray or any light ray is actually a transverse wave. And a transverse wave is made of crests going this way, troughs like this, crests, troughs, crests, troughs. Just imagine you're watching a wave move this way in a helicopter, and these are ocean waves. So you have crests going like this, right? So that's the same with this laser beam. So we got a wave front here, the first wave front, like this. It comes in, and you see that the wave front, because of the angle, doesn't enter all at the same time. This part of the wavefront right here enters the glass first. So this slows down first, and this stays moving in a fast velocity because it's still in the air up here. What does that do to the direction of travel? If you slow down this part and leave this going fast, it's going to turn it like this, right? That's going faster, so it's going to swivel that around like that. And then once it gets into the glass, now the entire wavefront's in the glass, and it'll go in a straight line like this. So that slowing down right here, because we went to a higher index, is what's responsible for the turning. So it's just because of n equals c over v. When we go from a high index to a low, as we learned in yesterday's video lesson, the light doesn't go straight, it bends away from the normal. For the same reason or a similar reason, but this time the opposite happens. Here's that wavefront coming down, and this part of the wavefront transitions into the next material first, but in the air with a lower index, we have a higher velocity. So this is actually speeding up, not slowing down, compared to this. What does that do to the direction of travel? If this speeds up, it's going to turn it like that, and then go off like that at a larger angle. So speed up first causes a turn of the wave. That's why it happens. That's why bending happens. The other thing that we're going to probably miss and maybe never do this year is an experiment on Snell's law. Now in that video that you should have watched, that I had in the Google stream, that link for, it showed you total internal reflection with this like curved piece of glass and light ray, a beam of white light. We would have used a very similar equipment, done a similar experiment to determine experimentally Snell's law. What we would have done is we would have made the white light come in at various angles, 0 degrees, 10, 20, 30, 40, up to 90. And we would have measured the angle that it goes in the water. If it comes in at 10 degrees in the air, in the water it'll be less because of Snell's law. And so you see all these, this is always 40, then it's 29 in the water. Always less because of the refraction, as I mentioned right here. But one thing that's kind of emphasized in the Regents is if that the light comes in at 0 degrees in the air, it'll be 0 degrees in the water. What does that look like physically? A lot of people will think, a lot of students, 0 degrees means it's like this because they're thinking the angles are measured with respect to the surface. No, the angles are always in optics measured with respect to the normal. So 0 degrees from the normal means it's actually on the normal. See, this is like 10 degrees apart. That's 0 degrees apart. That means the light's coming straight down on the surface. If light comes straight down on the surface, it doesn't matter what these indices are, the angle will be 0 degrees in the second substance. Whether high, low, high, it doesn't matter. And why is that the case? Snell's law. You plug in 0 degrees on this side, makes this whole side 0. The only way for this whole side to be 0 is for that angle to be 0 also. We have 0 equals 0. Doesn't matter what the two indices are. Okay, so that's one thing that you have to recognize as a pattern. And then as this angle increases to the maximum, the other one is increasing too. So at 10, as I mentioned, the angle here is not 10, it's slightly less, 7.5. So we keep increasing this increases, this increases, this increases. But when this gets to the maximum it could increase to, 90 degrees, this does not increase indefinitely. It will only increase for air and water to about 49 degrees. And that's the most the angle could be in the water if the light's coming from the air. Okay? So again, there's a limit here. That's the pattern we would have seen in the experiment. All right, so those are the couple holes that were left behind because unfortunately I forgot the one fact about speed of light causing Snell's law, causing refraction, and also because we couldn't do an experiment. We probably won't be able to do an experiment this year. Let's move on to today's information. What you should have seen in that video with the curved dish is that as you keep increasing the angle in the plastic, eventually there comes a point where the light no longer escapes the plastic. We have total internal reflection. All the light stays within the plastic. So, why does this happen? It's all happening because of Snell's law. So if we start in a higher index, zircon, in this case, light's going from zircon to alcohol. So this is bigger on this side. The alcohol's index is smaller, or maybe like in the video, you had plastic and air. The second index is smaller. That must mean for this equality to be preserved, the angle here has to be bigger. That's why the light bends away from the normal. So this ray 1 is showing that. See this light ray coming in? Light comes here, part of the wavefront speeds up first, and the light bends away from the normal, so the first light beam goes like this. If I increase the angle here, then by Snell's law, I have to increase the angle theta 2. Make this bigger, that gets bigger. Also, as we saw in our data table that I took away. But then what happens, so see what's happening, I'm going further from the normal, and this is getting closer to the surface. Eventually, if I pick an angle, a third angle, what would happen is this, according to Snell's law, would create an angle here such that this angle would be 90 degrees. In other words, the light, according to Snell's law, should bend along the surface 90 degrees from the normal. That doesn't happen. The light doesn't go along the surface. It actually then reflects. So see beam 3? Not here, not in the air. It stays completely in the zircon, the higher index. 100% reflection, because sunlight always reflects. We learned that even from these notes, right? Some light always reflects, and some goes through. But what we have here with ray 3 is 100% of the light bounces, none goes into the air. And if you go at an angle greater than this, what we call critical angle, beyond that angle, you keep getting 100% reflection. So this is ray 4. We could draw ray 5, and 100% of the light would stay in the zircon, none going into the alcohol. So rays 3 and 4 experience what we call total internal reflection. The light is trapped in the higher index. Always has to start in the highest, curving away from the normal, and then it doesn't, it stays in reflected. So that's the concept. That's what's happening with total internal reflection. But you also have to be able to calculate the angle at which this happens. How many degrees can we go before no light can go into the alcohol? This is how you do it. So, calculating theta critical for the alcohol zircon boundary. Again, the light must start, in the alcohol, not in the alcohol, in zircon. Got to change this to higher. I don't know what I was thinking. Okay, so it has to start in the zircon, the higher index always. So I imagine the light coming in zircon at the critical angle, and for now I'm going to pretend that it refracts along the surface here. In other words, theta from the normal is 90 degrees. When you're calculating the critical angle, theta 2 is always going to be 90 degrees to calculate this critical angle. And then we just use Snell's law. N1 sine theta 1 equals N2 sine theta 2. In material 1, we are in zircon, the higher index with theta critical. In material 2, we have the alcohol's lower index and the 90 degrees together. And then we just have to solve for theta critical, which is what this is showing. I divide both sides by 1.92. I punch this all on a calculator, I get 0.708. And then I do the inverse sine of that, and I get 45.1 degrees. A reminder on the Regents, you leave these little degrees off, you're going to get 1 out of 2, a 50% on this problem. So everything here has to be here. I guess you don't need this step here, okay? That step doesn't need to be there. But the equation, substitution with units, the little degree, the indices don't have units, and then the answer, that's the 2 points. All right, so that's how you calculate the critical angle. Higher index, theta critical, lower index, 90 degrees into Snell's law. Now, I also want to highlight some applications. So here, one application, fiber optic cable. Many of you have fiber optic internet at home. Fiber optic transmits internet signals with light. But think about this. If I have a laser beam and I flash it like Morse code, and so I hit the little button on the laser pointer, how do I get the light to go out of this room that I'm in, through the various neighborhoods, across the country, around all the trees and the people in the way, and then go into someone else's house, and then that person can see that light beam. Light travels in a straight line, so I can't just shine this laser and expect that to happen. What we do is we have what we call fiber optic cables. Again, the fiber optic cables, I have some, they're at school, and so I can't show you them. But imagine just like hair. They look like little hair, plastic hair. And it just, you feel it, it feels soft, you could feel it, it feels like essentially human hair. It's a very thin piece of plastic. And it utilizes total internal reflection. You shine light into one end, and then this has got some kind of index like 1.5 or 1.7, whatever the index of plastic is, it's surrounded by air of index 1.0. So we're in a high index, we're going toward a low index. Light would bend away from the normal if it could get out of the plastic, but this angle is beyond the critical angle, so we get 100% reflection. It's as if this outside is coated with a mirror, but it's not. You would see that if I handed you the fiber optic, it would just look like a piece of plastic. But we still have 100% reflection here. So then it comes to surface 2, and it hits here at an angle greater than the critical angle, we get 100% reflection. Once again right here, it hits at an angle greater than critical angle, 100% reflection according to law of reflection. Again, 100% reflection, 100% reflection, and then it comes out the end. So look, I shine the laser this way, and it comes out that way, because it's piped through this fiber optic cable. So fiber optic cable is like a pipe for light. That's what this says. Theta 1, Theta 2, Theta 3, Theta 4, and Theta 5 are all greater than greater than 90, greater than the critical angle. A lot of mistakes today. I don't know what happened. Greater than theta critical. At each point, the light contacts the cable air interface. 100% of the light reflects. The light is piped around corners. So that's how you can get light to go and give you internet signals. A second application, the periscope. So I have a little periscope, a couple at school, but you may have seen movies with submarines. You know, someone's looking into a device, and then the tube extends beyond the surface of the water. Maybe this is the surface of the water here, and they could see down in the submarine. Okay. Another application for periscope is with old tanks. Before they had video cameras and monitors, obviously you want the soldiers behind steel plates, but if you put everyone behind a steel plate, how does anyone see where they're going? But if you put a little hole in that steel plate, well, then maybe you get a sniper who's really good and could shoot a bullet right into somebody's eye who's looking out the hole of the tank. Not good. So what you do is you make a steel plate like this. The people are behind here, and you put a plastic up like this. And then the light from the surroundings goes and reflects along this plastic like this, and the person's eye right here can see outside the metal plate of the tank, or above the water surface of the submarine. How does that happen? The light comes in here, goes into this plastic, and see how it hits this? This is plastic air. And the interface here, so theta is greater than theta critical, 100% of the light reflects here. Same here, greater than the critical angle, 100% reflects. Reflection, reflection, out. No mirrors here necessary. Just total internal reflection, because theta 1 and theta 2 are both greater than theta critical. 100% of the light reflects. One last little note, that one of the homework problems, they give you the wavelengths of the light in the two materials, and it's a little trick. Every year it gets people. But if I start with this, and I'm solving for theta critical, right? Oops, I should have been solving for theta 1. Oh, another mistake. Okay, well, anyways, I'm solving for the angle here. And if I divide both sides by n2, and then I would take the inverse sine of both sides, remember that theta 1 over theta 2, from our reference table, I mean n1 over n2, if you have the ratio of the indices, that's the opposite ratio of the wavelengths. So 2 over 1 is the ratio of wavelength 1 over 2. Here I have 1 over 2, so I replace that with wavelength 2 on top, wavelength 1 on top. So I could do Snell's law problems if I knew the wavelengths in the two materials also. All right, so that's total internal reflection, right? So you use Snell's law, plug in higher index with theta critical, lower index with 90 degrees, solve for theta, you get the critical angle, where beyond that 100% of the light stays in the higher index material. There's one last video I would recommend you watch. It's only 1 minute long, and it's a very beautiful video of someone using total internal reflection to trap a laser in a water beam. And take a look at it, and you'll really see total internal reflection happening in real time. Well, not real time, but with a video. And as I said, it's nice to watch. All right, so that's total internal reflection. I'll see you in the next physics video.